a shallow dish, and in it a black disc about the size of a coin, matte, faintly rough, like a fragment of a broken plant pot. Pour liquid nitrogen over it, and the whole dish boils and fogs for half a minute. Now bring a small square magnet down on a plastic rod and let go. It stops about 3 millimeters above the surface and stays there in the cold fog, with nothing underneath it. Touch it with the rod and it spins, slowly, in the same place, for the best part of a minute. Now lift the dish and turn it upside down. The magnet does not fall. It hangs below the disc at the same distance, held onto nothing.
Which is the whole hour standing in a dish, and it follows from the sentence we closed on. The particles that have to pair are charged. Start with what the disk is. Yttrium, barium, copper and oxygen, fired into a ceramic. Liquid nitrogen boils at 77 Kelvin, and that ceramic stops resisting at about 93, so it is comfortably below its transition. And below the transition, it refuses to let a magnetic field into its interior. Your magnet's field is thrown out, the throwing is mutual, and the magnet is held off the surface. That is the Meissner effect, and it is the property that makes this a state of matter rather than an extremely good wire.
Take the second half of what I described, though. I turned the dish over, and the magnet hung underneath it. Expelling a field is a push. What pulled?
Nothing pulled, and the sentence I just gave you is wrong on exactly the part you are pressing. Expulsion is repulsion, and only repulsion. It could push the magnet up. It could not stop the magnet sliding off sideways, and it certainly could not hang anything below a plate. What locks that magnet is the opposite of expulsion. Some of its field does get in thin tubes, and the tubes are stuck where they are. That needs an object we have not built yet. What survives from my first answer is the expulsion itself, and the expulsion is where we have to start, because for 22 years nobody knew it happened.
22 years after what?
After the discovery. Kamerlingh Onnes in Leiden had liquefied helium in 1908, which made him the only person on Earth with access to a few degrees above absolute zero, and he went looking for the answer to an argument. What does the electrical resistance of a pure metal do as absolute zero approaches? 3 positions. Meissner from the 1860s, it flattens out at whatever the impurities leave behind. Dewar, it slides smoothly to zero. Kelvin in 1902, it falls, turns round, and goes to infinity because the electrons freeze onto the atoms.
And the answer was none of the 3.
None of the 3, though it took him half a year to see that. On the 8th of April, 1911, with a mercury thread in a helium bath, he pumped down to about 3 Kelvin, and the resistance went to something his instruments could not distinguish from nothing. The notebook entry is 3 words of Dutch, mercury practically zero, and he read it as his own prediction confirmed, a pure metal sliding smoothly to zero, exactly as Dewar said. The same afternoon, the helium stopped boiling and quietly shrank instead. The lambda point crossed and unnoticed. The cliff arrived later. In May, the resistance reappeared between 4.1 and 4.2 on the way up. And on the 26th of October, he drew the curve. Within 100th of a degree, at 4.2 Kelvin, from unmeasurable to 1/10 of an ohm. Nothing slides like that. He suspected a short circuit first and looked for one.
How do you establish that a resistance is 0 rather than very small? A voltmeter reading nothing is a statement about the voltmeter.
You stop measuring voltage and start measuring time. Onnes wound lead wire into a closed loop, cooled it, drove a current round it with a magnet, took the magnet away and watched the current with a compass needle. 1914. No detectable decay in an hour. And in 1932, 6 years after his death, his chief technician Gerrit Flim carried a portable Dewar with a lead ring in it from Leiden to London and set it on a bench at the Royal Institution. still running 200 amps with nobody driving it.
So the field settles on the obvious name, a perfect conductor. And I want to push back on the way you introduced expulsion, because I do not see that it is a second fact. If a material carries any current at no cost, then when you bring a magnet near it will carry exactly the current needed to cancel that field inside itself. Lenz's law with nothing to stop it.
Run it carefully, because the answer depends on something you have not put in. In a perfect conductor, the electric field inside must vanish. Any field at all would drive an infinite current. And a vanishing electric field means, by Faraday, that the magnetic field inside cannot change. Not that it is zero, that it cannot change. Now do 2 experiments in different orders and watch what that gets you.
First order, cool the sample with no field anywhere, then bring the magnet up. The interior field started at 0 and is not allowed to change, so it stays 0. The field is kept out. Second order, bring the magnet up while the sample is warm, so the field soaks right through it, and then cool. At the moment it becomes perfect, the interior field is frozen at whatever it was. So a perfect conductor ends up with a field inside it.
A perfect conductor ends up with a field inside it, and which of the 2 states you get depends on the order you did things in. That is the prediction, and it held the subject for 22 years. Walter Meissner and Robert Ochsenfeld ran the second experiment in 1933. Tin and lead cylinders, field applied first, then cooled, and mapped the field in the gap between them. And the field outside went up as the samples went superconducting, which is what happens when flux is squeezed out of somewhere and has to go elsewhere. The interior emptied.
So a superconductor throws the field out even when it was already inside. It does not merely refuse to admit a change, it undoes the past.
Say what that buys, because it is the largest single idea so far, and it is not about magnets at all.
It buys history independence. A perfect conductor's state depends on the route you took, so it is not one state, but a family of them, labelled by what you did. A superconductor arrives at the same state whichever way you come, so it is a thermodynamic state fixed by temperature and applied field and nothing else, which means I can do thermodynamics on it, free energies, a phase boundary.
A phase in the sense of everything we did with the ferromagnet, a state of matter with a free energy you can compare against the normal metals, and a transition line in the temperature field plane you can measure with a thermometer and a coil. Zero resistance alone would never have given you that. Zero resistance is a kinetic accident. Expulsion is a statement about equilibrium. It is why superconductivity was available to Landau's machinery 7 years before anybody knew what the electrons were doing.
What do you throw away to get it? Field expulsion cannot be free.
It is not. Pushing a field out of a volume costs energy. The field has to go somewhere, and the screening currents have kinetic energy. So the ordered state is only worth having while the saving from being ordered beats that cost. Turn the field up, and at some value the cost wins and the material goes normal. In lead, that critical field is about 8/100ths of a Tesla, which an ordinary iron magnet beats. Superconducting magnets exist because that sentence has an exception.
1911 to 1957 is 46 years, and the list of people who tried and failed is absurd. Einstein, Bohr, Heisenberg, Born, Feynman, Landau. What was actually in the way?
2 things, and the second is structural rather than a matter of anybody being insufficiently clever. The first is obvious and looks fatal. Electrons repel each other. Whatever this state is, it is electrons doing something collective, and the only force between them points the wrong way. The second is a scale problem, and you can see it before I say anything. Give me the 2 energies.
The transition temperatures are a few Kelvin, and the Fermi energy of a metal is a few electron volts, which in temperature units is tens of thousands of Kelvin. So the ordering happens at something like a 10,000th of the only energy scale a metal has.
A 10,000th and sometimes a 100,000th. Now ask where a number that small can come from. The smallest energy ratio a metal offers you is the phonon scale against the Fermi energy, and that is 1 part in a few hundred. So the answer cannot be a small correction to the Fermi energy. Small corrections come out as a percentage, not as a factor of 10,000. Whatever produces the transition temperature has to produce it by some mechanism that manufactures smallness. And the only function that turns a modest number into a tiny one is an exponential.
You are telling me the answer before the argument.
I am telling you the shape of the answer, which is how you should always start. And the shape has a consequence that explains the 46 years. Suppose the answer is some energy times e to the -1 over a coupling constant. Now try to find that by perturbation theory. Expand in powers of the coupling, take the first term, the second, the third. Every one of them is 0. That function is flat to all orders at the origin. Perturbation theory was the only general tool anybody had, and the answer was invisible to it at every order.
So it was not that they were slow, it was that the object is not reachable from where they were standing. Then what broke the deadlock? Because a structural obstruction does not usually give way to more thinking.
An experiment nobody had expected to matter. 1950. 2 groups, independently, Emmanuel Maxwell at the National Bureau of Standards and Reynolds, Serin, Wright and Nesbitt at Rutgers. Both had separated isotopes of mercury for the first time, a post-war luxury, and both measured the transition temperature against which isotope the sample was made of. Chemically identical. Same electrons, same lattice spacing, same everything except the mass of the nucleus. And the transition temperature moved.
Which it has no business doing. The nucleus sits there being a positive charge. Unless the only way mass can enter is through motion, and the only thing in a crystal whose motion depends on ionic mass is the lattice vibrations. A vibration frequency goes as the square root of a stiffness over a mass, so a heavier ion vibrates more slowly, as 1 over the square root of its mass. Did the transition temperature go the same way?
Exactly that way. Transition temperature times the square root of the isotope mass came out constant, to within the errors, an exponent of 1/2. So the transition temperature is proportional to a phonon frequency. And Herbert Froelich, the same year, working from theory with none of that data, had already argued that the coupling between electrons and lattice vibrations was the place to look.
The phonons, which is a genuine shock, and I want to say why. In every treatment of a metal I have met, the ions are a static background, providing a periodic potential, and their vibrations are a nuisance that scatters electrons and makes resistance. They are the reason a metal is imperfect. Now they are the mechanism of the most perfect thing a metal does.
The same coupling, doing both jobs. Scattering off lattice vibrations gives copper its resistance at room temperature. At low temperature, the same coupling binds the electrons into the state that has none. Nothing was added to the metal.
Then how does a vibration of positive ions turn a repulsion between 2 electrons into an attraction? I can see that the ions respond to an electron. I cannot see how the response outlives the repulsion.
By being slow, and the slowness is the entire trick. Picture 1 electron traveling through the lattice at the Fermi velocity, about 1,000,000 meters a second, roughly 1/3% of the speed of light. As it goes past, it pulls the positive ions towards its track. Now, how fast can they answer? An ion is thousands of times heavier than an electron. The fastest a lattice can rearrange itself is 1 period of its own highest vibration, and for a typical metal, that is around 10 to the -13 of a second.
So the ions arrive late. Multiply the two. 1,000,000 meters a second times 10 to the minus 13 seconds is 100 nanometers, which is hundreds of lattice spacings. The electron is enormously gone by the time the ions have finished moving towards where it used to be.
What is left behind is a thin tube of country where the positive ions are packed slightly closer than they should be. Excess positive charge sitting in the wake, persisting for that same tenth of a picosecond. Now bring a second electron along and ask what it sees.
It sees positive charge and is drawn in. So the second electron is attracted to the trail of the first rather than to the first. And they are never in the same place at the same time, which must be why the direct repulsion does not simply cancel it.
Delayed is the word the subject uses. Retarded. Two electrons 100 nanometers apart barely see each other's charge because the other electrons have screened it away within a fraction of a nanometer. But both talk to the lattice, and the lattice keeps its memory for 100 nanometers worth of travel. So the net interaction between two electrons whose energies differ by less than a phonon energy comes out attractive. I am asserting that last step rather than deriving it. The calculation is Frohlich's, then Bardeen and Pines in 1955, and it shows the phonon term beating the screened Coulomb term precisely in that low-energy window and nowhere else.
Give the mechanism a name I can hold, because the phonon-mediated attraction tells me nothing about what happens.
Overscreening. The lattice's job is to screen the electron's charge, to surround it with enough positive response to cancel it. Because the response is sluggish, it overshoots, arriving after the charge has left, so in the wake there is more positive than there was negative. The screening does not cancel, it overcorrects, and the overcorrection is the attraction. A heavy door that keeps swinging after you have gone through it.
And that 100 nanometers has to be the size of whatever gets bound, if anything does.
It is, and hold that number against your intuition about what a bound pair should look like. In aluminium, the pair turns out to be about 1.5 microns across. That is not two particles holding hands. That is two particles in different postcodes, correlated across a distance in which several million other pairs are also sitting, overlapping them, sharing the same volume. Whatever this state is, it is not a gas of little molecules.
An attraction then, and a feeble one. Feeble how? Against what?
Against everything. The attraction lives on the phonon scale, a few hundredths of an electron volt at most, set against a Fermi energy of several electron volts, and the dimensionless coupling that comes out is typically a quarter or a third. So here is the question Leon Cooper asked in 1956, and it is deliberately small. Take the filled Fermi sea and freeze it, so those electrons may do nothing. Add two more on top, just above the surface, attracting each other weakly. Does anything happen?
My instinct says no, and I can defend it. Two particles in 3 dimensions with an attractive well between them do not automatically bind. A shallow well has no bound state at all. You have to make it deep enough before the first level drops below the rim, and there is a genuine threshold. So a weak attraction between two electrons gives me nothing until it exceeds some size, and a residue left over after screening is nowhere near it.
Everything in that is correct in empty space, and the conclusion is wrong here, and the reason is the one thing you were told to ignore and did. Start with why the threshold exists, because the usual statement of it hides the mechanism. To build a bound state, you superpose free states. You make a localized object out of extended ones. So the question is how many cheap free states there are to build with. In 3 dimensions, the number of states per unit energy vanishes as you approach zero energy, going as the square root of it. There are not enough cheap states, and a weak attraction cannot afford the expensive ones.
So it is a counting statement, not a force statement. And you are about to tell me the counting is different when there is a C underneath.
Completely different, and it is one substitution. your two extra electrons cannot use any state below the Fermi surface because those are occupied and exclusion is not negotiable. So the states available to them do not start at zero energy. They start at the surface of the sea. And the number of states per unit energy at that surface is not vanishing. It is a finite constant, the density of states at the Fermi level, and it is large. The sea hands you a problem where the cheap states are uniformly plentiful, all the way down to no cost at all.
Which is two-dimensional counting rather than three-dimensional, a constant density of states, and in 2 dimensions any attractive well binds, however shallow. That is the other half of the standard result. So the sea has removed the threshold.
And you can watch the mathematics do it. Adding up those available states with a constant density and an energy in the denominator gives a logarithm of the width of the phonon window over the binding energy. A logarithm has no ceiling. However small the coupling, you can always make the logarithm big enough to match 1 over it, because it grows without limit as the binding energy goes towards zero. So there is always a solution, a bound pair for any attraction whatsoever, with a binding energy that is the phonon energy times e to the minus something over the coupling.
The exponential you promised 20 minutes ago arriving from the counting rather than from anything about phonons. Say the one-sentence version so I can carry it, because this is the thing I was wrong about.
The Fermi sea is not a spectator. Its only role is to block the low-lying states, and by blocking them, it guarantees a supply of states at zero cost that a two-particle problem in free space does not have. And that supply is what defeats the smallness of the attraction. Weak attraction plus scarce states is nothing. Weak attraction plus an endless flat supply of states is a bound state every time.
Where does that leave the sea I was told to keep frozen? Because if a pair of electrons at the surface gains energy by binding, then every pair of electrons at the surface would gain energy by binding, and there was nothing special about the two I put on top.
Nothing whatever. And that is why Cooper's result is called an instability rather than a bound state. The conclusion is not that two electrons pair up, it is that the Fermi sea, the object the whole theory of metals is built on, is not the ground state at all. Given any attraction at the surface, however small, it is unstable against pairing, everywhere on the surface, at once. The calculation destroys its own starting assumption.
And a state where everybody is paired at once is a different problem from a state with one pair in it.
A far harder one, because the pairs overlap by millions and cannot be treated as separate objects. That is what Bardeen, Cooper and Schrieffer solved in the first half of 1957. Schrieffer with the crucial guess about the form of the wave function made on a New York subway train in January as a graduate student. The short announcement appeared in Physical Review in April, the full paper on the 1st of December. Bardeen already had a Nobel Prize for the transistor, the second came in 1972, and he is still the only person with 2 in physics.
Build me the state then. What am I picturing?
Start with which electron pairs with which, because it is not arbitrary. 2 constraints pick it out, and both are about counting. If a pair is to have any freedom to scatter into other pair states, and that scattering is the attraction doing its work, then all the pairs must share the same total momentum. And the choice that maximizes how many partners are available is 0. So a pair is an electron with some momentum and an electron with exactly the opposite momentum, 2 points on the Fermi surface directly across from one another. Opposite spins as well, up with down.
Antipodal partners. Every point on the surface married to the point diametrically opposite. And every one of those marriages has the same total momentum, namely none, so they can all exchange partners with each other freely. And the spins are opposite because both electrons are in the same orbital state, which Pauli permits exactly once.
That is the picture. Now the state itself, and here it stops resembling anything in a first course. Take one such pair state, a particular momentum and its opposite. In an ordinary metal, it is either occupied or it is not. Below the surface occupied, above it empty, and the boundary is sharp. In the superconductor, each pair state is in a superposition of occupied and empty, with an amplitude for each. And the phases of all those amplitudes across the entire Fermi surface are locked to one another.
That is what makes it an order parameter, rather than a filling. One common phase agreed across the whole surface, and nothing measures it. The wine bottle again, with the marbles somewhere in the trough. But what is the physical consequence? A superposition of occupied and empty sounds like bookkeeping.
The consequence is measurable, and it is the central quantity of the hour. Ask what it costs to disturb this state, to take one electron out of the arrangement and make it an independent excitation. In a normal metal, an electron just above the surface costs almost nothing. You can excite that metal for any budget you like, and there is no flaw to its excitations. In the superconductor, breaking a pair means paying a minimum. There is a cheapest excitation, and its price is finite.
A gap. The word from the helium hour, where Landau read one off a heat capacity.
The same word and the same experimental signature. An exponential in the low-temperature heat capacity rather than a power. The shape of the spectrum is worth a sentence. In a normal metal, plot excitation energy against distance from the Fermi surface and you get a V, a straight line down to zero at the surface and back up. In a superconductor, that V is pushed apart into a hyperbola. Far from the surface, it lies on the old lines. Right at the surface, where the energy used to be zero, it is now the gap.
How much of the metal is that? Because if the answer is a hair's breadth of a shell, I want to know how it can be responsible for something as gross as levitating a magnet.
It is a hair's breadth. The gap in aluminium is about 0.2 of a millielectron volt, against a Fermi energy of about 12 electron volts. Roughly 1 part in 100,000 of the electrons are involved. And that is the emergence claim at its sharpest. A state of matter with new laws, made by rearranging 1 electron in 100,000 in a shell too thin to draw.
Then give me the equation that fixes the gap, because so far, the gap is a name for something I have asserted exists.
We build it in one move, and the move is a loop. Ask what determines the gap at one point on the Fermi surface. The answer is the attraction acting between that pair state and all the others. The gap there is the interaction strength times the total amount of pairing going on everywhere else. So we add up, over the whole Fermi shell, how much pairing each pair state contributes.
And how much is each contributing?
That depends on how thoroughly mixed it is between occupied and empty, and that is set by where it sits. A pair state far below the surface is simply full. No mixture, no contribution. Far above, simply empty. Nothing again. Only the states within a gap's worth of the surface are genuinely half one thing and half the other, and those are the ones that contribute. So the number of contributing states and how strongly each contributes is governed by the size of the gap.
Which is what I was trying to compute. The gap appears on the left of the equation, and it is buried in every single term on the right.
That is the BCS gap equation, and that is the whole of its character. It is not a formula for the gap. It is a condition the gap has to satisfy. The gap exists because pairs form, and pairs form because there is a gap. Neither half of that comes first. They come together or not at all, and the equation states that the system finds an arrangement in which they are consistent.
Which sounds circular in a way that ought to make me suspicious. What stops the answer being zero?
Nothing stops it, and the zero is always a solution. Put no gap in, and you get no gap out, which is the ordinary metal. The question is whether a second solution exists, and whether it is lower in energy. So do what you do with any self-consistency. Assume the gap is not zero and divide it out of both sides. Everything on the left cancels, and you are left with the number 1. and on the other side, the coupling multiplied by a sum over the Fermi shell.
And I know what that sum is, because it is the same counting as before, a constant density of states, an energy in the denominator, integrated over the phonon window. It gives a logarithm of the window's width over the gap.
1 equals the coupling times that logarithm. Now solve it in your head.
The logarithm has to equal 1 over the coupling, so the ratio of the phonon energy to the gap is e to the 1 over the coupling, and the gap is the phonon energy times e to the minus 1 over the coupling, which is the shape you told me to expect an hour ago, arriving with everything specified.
With everything specified and nothing fitted. Put a coupling of 1/4 into that, and the exponential gives you about 1/50th. Take a phonon energy scale of a few hundred Kelvin, and you land on a transition temperature of a few Kelvin. The 10,000th we could not account for is manufactured, entirely, by that exponential. Not by any small quantity in the metal, but by the fact that the answer is non-analytic in the coupling, which is also precisely why nobody found it by expanding in powers of anything.
2 things fall out of that before I ask for them, and I want to check both. The prefactor is the phonon energy, and the exponent contains only the coupling, nothing about the ions. A phonon energy goes as 1 over the square root of the ionic mass, so the transition temperature must too, with an exponent of exactly 1/2, which is the isotope measurement, predicted rather than accommodated.
Predicted rather than accommodated, and it was the strongest early evidence there was. What is the second?
That the coupling ought to cancel out of some ratio. If the gap is a phonon energy times an exponential, and the transition temperature is a phonon energy times almost the same exponential, their ratio contains neither. It should be a pure number, the same for every superconductor, whatever it is made of.
A pure number, and the theory says twice the gap is about 3.5 times the transition temperature in energy units. Aluminium comes in at 3.4, tin at 3.5, indium and thallium within a few percent. Lead and mercury run high, near 4.5, and the reason is known. Those two are strongly coupled, so the small coupling assumption is failing, and Eliashberg's stronger version in 1960 accounts for that excess.
How do you see a gap of 0.2 of a milli-electron volt? That is a very small thing to go looking for.
With a voltage. 0.2 of a milli-electron volt is 0.2 of a millivolt, a number a bench voltmeter reads without complaint. So build a sandwich, a strip of ordinary metal, a layer of oxide a nanometer or 2 thick, and a strip of superconductor on top. Electrons can tunnel through the oxide, feebly. Apply a voltage and measure the current.
And the current tells me about the states on the far side, because an electron can only tunnel into somewhere it is allowed to be. Below the gap there is nowhere to land, so no current at all, not a small current, none. Raise the voltage until the electrons arrive with enough energy to reach the first available states, and the current switches on. So the switch-on voltage is the gap, in volts.
In volts. Ivar Gieva did that in 1960 at General Electric. Aluminium, aluminium oxide, lead, and read the gap off the trace. Now push past the switch-on, because the shape of the curve carries something the threshold does not. What happened to the states that used to live inside the gap?
They cannot have been destroyed. The number of states is fixed. Opening a gap does not delete room, it moves it. So the states that were in the gap have been pushed out to the edges and must be piled up there, which means just above the switch-on there should be an excess. More states per unit energy than the normal metal had, not fewer.
A sharp peak right at the gap edge, and the slope of the current against voltage traces the density of states point by point. It is there in Gieva's data, spike and all, and he shared the Nobel Prize in 1973. One caution, and we come back to it. A gap is not the order parameter. A semiconductor has a gap and does nothing interesting. What makes this state superconducting is phase coherence across the sample. The gap is a consequence.
You said 7 years earlier somebody had done this without knowing any of it.
Vitaly Ginzburg and Lev Landau, 1950. And the recipe is one you can now recite. Write the free energy as a series in a small order parameter. Let symmetry delete what it deletes. Let the quadratic coefficient change sign at the transition. Let the quartic term stop the runaway. For helium, the order parameter was a complex function of position, with a further term charging for it varying in space. Ginzburg and Landau wrote the same thing for a superconductor, with exactly one difference.
The order parameter is charged. What does that force?
It forces the gradient term to change, and the reason is one of the tightest arguments in physics. The phase of a charged field is not measurable on its own, and not even meaningful on its own. You may redefine it differently at every point in space, provided you shift the vector potential of the electromagnetic field to compensate. That is a gauge transformation, and nothing physical may depend on it. So a term that charges for the phase varying in space is illegal. You could make the phase vary as much as you liked by choosing a silly gauge.
So the only legal object is the phase gradient measured against the vector potential. The two together in a combination that is unchanged when you shift both. And that combination has to appear everywhere the gradient appeared before.
Everywhere with a factor in front of the vector potential that is the charge of whatever carries the phase. Hold on to that factor. It is the number this hour is heading for. And now, before the charge does anything dramatic, ask what the equation gives you in the simplest case, which is a piece of superconductor with an ordinary metal butted against one end. Not vacuum. The order parameter does not care about vacuum. It cares about a normal metal.
The same as helium gave, I would expect. The order parameter is forced to 0 at that junction. The gradient term hates that, and the quartic term is relieved by it, and the balance sets a distance over which it recovers. A healing length under a different name.
The coherence length, the size of a pair, arriving from a completely different direction. Your 100 nanometers for a typical metal, and for something as weakly coupled as aluminium, the micron and a half I made you swallow earlier. But now the charge earns its keep, because a charged order parameter gives you a second length that helium had no way of producing. A varying phase in a charged system is an electric current. A current makes a magnetic field, and a magnetic field pushes back on the current that made it. Follow that round the loop and tell me what happens to a field trying to get into the material.
It gets screened. The field enters at the surface, sets up currents, and those currents produce a field opposing it, so it dies as you go in. And if the response is proportional to the field, it dies exponentially over some distance. Which is the Meissner effect with a number attached. The field is not thrown out by fiat, it is screened out over a length.
The penetration depth, and Fritz and Heinz London had written the equation for it in 1935. 2 years after the expulsion was discovered. In aluminium, it is 16 nanometers. In the ceramic in your dish, it is a few hundred. Either way, the field does get in, just not far. And now you have two lengths in the same theory, and the entire remaining structure of the subject is the ratio between them.
Why should a ratio of two lengths matter? They are both small and both measured in nanometers.
Because the ratio decides the sign of a surface energy, and that decides whether a material wants boundaries or hates them. Picture a region of normal metal inside a superconductor and walk across the wall between them. Two things happen over that wall, over different distances. The order parameter has to climb from 0 to its full value, and that takes a coherence length, over which you are paying because you have not got the ordering energy yet. The magnetic field has to die from its full value to nothing, and that takes a penetration depth, over which you are gaining because you have not yet paid to expel it.
So it is a race between a length over which the wall costs and a length over which it pays. If the coherence length is longer, the cost region is wider than the gain region, the wall has positive energy, and the material wants as few walls as possible. If the penetration depth is longer, the wall has negative energy, and the material wants as many as it can get.
The dividing ratio is penetration depth over coherence length, equal to 1 over the square root of 2. Your argument said the two lengths simply had to match, and the exact sum moves the line by that factor. Below it, type 1. Lead, tin, mercury, aluminium, nearly every element. It keeps the field out completely, tolerates no interior boundary, and when the field gets too strong, it gives up all at once. Above it, type 2. And a type 2 superconductor, faced with a field it cannot afford to exclude, does not give up. It lets the field in the thinnest tubes it can manage, because every tube is now a bargain.
How thin can a tube be? Something has to stop it subdividing forever, or it would shred itself into nothing.
Something does, and you have already met it. Each tube is a place where the order parameter goes to 0, with the phase winding once around it. A vortex, the same object that ran down the axis of rotating helium with the same reason for existing. The phase can only be undefined where the magnitude vanishes. And the winding is a whole number of turns, so the flux the tube carries cannot be anything you like. One indivisible unit, and that unit is what we are about to measure.
Who worked that out? Because a lattice of flux tubes is a very specific thing to predict from a free energy expansion.
Alexei Abrikosov in Moscow, and the story is a warning about deference. He had the solution in 1953, took it to Landau, and Landau did not like it, so he sat on it and published in 1957. A lattice of flux lines, each carrying one quantum, packing closer as you raise the field, and he got the shape wrong. A slip in the arithmetic gave him a square. Kleiner, Roth, and Ortler found the triangle 7 years later, which is what mutually repelling lines in a plane always do, and what the vortices in a rotating bucket of helium do. Uwe Essmann and Hermann Treubel photographed it in 1967, and Abrikosov and Ginzburg shared the Nobel Prize in 2003 with Anthony Leggett.
And this is where you owe me the magnet in the dish.
This is where I pay it. The ceramic is an extreme type 2. Its penetration depth beats its coherence length by about 100, so your magnet's field is not expelled. Most of it threads the disk as a forest of vortices. And a real ceramic is full of defects, grain boundaries, oxygen vacancies, and a vortex core sits more cheaply on a defect than in perfect material, so the lines get stuck, pinned. To move the magnet, you would have to drag every one of those flux lines out of the site it settled into. The magnet is not balanced on a cushion of repulsion. It is bolted to the disk through thousands of millions of pinned threads of magnetic field, which is why it holds a position, why a nudge makes it spin rather than slide away, and why it hangs there when you turn the dish over.
And the same pinning must be what makes superconducting magnets possible, because a vortex that can move is a vortex that dissipates.
Exactly the same, and it is why the wire in a hospital scanner is deliberately made dirty. A current pushes sideways on the flux lines. If they move, they dissipate, and your zero resistance is gone. Pin them, and the current flows up to the field, where the pinning gives way. Niobium titanium carries the 8 1/3 Tesla dipoles of the Large Hadron Collider against 8/100ths of a Tesla for lead.
You have used the phrase, the charge of whatever carries the phase, twice now, without saying what it is, and I think that is deliberate.
Entirely deliberate, because it is measurable, and the measurement settles the microscopic question without mentioning phonons, gaps, or Bardeen. Rerun the ring. In helium, you took a closed loop inside the fluid, walked round it, and required the phase to return to itself. Do it here, in a thick ring of superconductor, with the loop deep inside the metal rather than near the surface.
Why deep inside? That was not a condition before.
Because of the penetration depth. Currents live within a penetration depth of the surface. Deeper in, there is no current at all. Take your loop down there, and the current on it is exactly zero. Now do the argument.
The order parameter is single-valued, so going once round the loop, the phase must come back to the same angle. It has wound by a whole number of turns. And what I may add up round the loop is not the phase gradient by itself, because that is not gauge invariant. It is the combination, phase gradient minus the charge times the vector potential. That combination is the current, up to a factor, and you have just told me the current is zero on this loop. So the two pieces cancel each other everywhere along it.
Keep going. Add each piece up separately.
Adding the phase gradient round the loop gives the total winding, a whole number of turns. Adding the vector potential round a closed loop gives the magnetic flux threading it. That is what a vector potential is for. So, the flux through the ring is a whole number times Planck's constant over the charge that carries the phase, quantized, with a quantum set by that charge.
Which is a measurement waiting to be done. Trap flux in a small ring, change it, and read off the spacing of the allowed values.
And the spacing came out at Planck's constant over twice the electron charge.
Over twice the electron charge. Two groups, independently, back to back in the same volume of Physical Review letters in 1961. Bascom Deaver and William Fairbank at Stanford, a tin film electroplated onto a copper wire 13 microns across. Robert Doll and Martin Narbauer in Munich, a lead film on a quartz cylinder read from the torque on a suspended fiber. And the quantum is about 2 times 10 to the minus 15 Webers, the Earth's field through a square roughly 6 microns on a side.
Say what the two proves and say it narrowly. In helium, the quantum of circulation contained the mass of one helium atom, and that told us the thing carrying the phase was a single atom. The identical argument here contains the charge of the thing carrying the phase, and the charge that comes out is 2 electron charges. So the object whose phase is coherent across the sample is not an electron. It is a pair.
A pair, measured. Not inferred from a fit, not extracted with a model the way an effective mass is. A charge, read off the period of an oscillation, and it comes out at 2. Everything else, the retarded attraction, the instability, the self-consistent gap, is an account of why pairs form. That number says they exist.
Had anybody predicted the 2 before it was measured? Because a factor of 2 arriving unannounced would be a very different story.
The theory was 4 years old and said pairs, so people were braced for it. London had guessed flux quantization in the 40s, but with 1 electron charge, before pairing existed as an idea. Ginzburg had noticed, comparing his theory with the data, that the fit wanted about twice the electron's charge and did not press it. And Lev Gorkov derived the whole Ginzburg-Landau construction from BCS in 1959, with the charge coming out as 2e.
Is there a second way to see the 2, in case the trapped flux experiments were sensitive to something about the geometry?
William Little and Ronald Parkes, 1962. Take a thin-walled superconducting cylinder, sit it at its transition, and sweep a field along its axis. The winding the phase is forced into costs kinetic energy, least whenever the flux is near an allowed value, so the transition temperature itself oscillates, and the resistance ripples with it. Nothing trapped, and the same period.
There is a debt outstanding from the ferromagnet. Break a continuous symmetry, and you get a mode that costs arbitrarily little. magnons in iron, sound in a crystal, the phase mode in helium that held up the whole edifice. A superconductor breaks the same phase symmetry helium does, so where is its gapless mode? It should have one, and I have not heard it mentioned all hour.
It does not have one, and finding out why is the deepest thing in this hour. Ask what a long wavelength twist of the phase physically is here.
A current, since the phase gradient is the current, and in a charge system, a current that varies from place to place piles charge up somewhere, which costs Coulomb energy, and the Coulomb interaction is long-ranged.
Which is the condition written into the Goldstone theorem and then quietly forgotten by everyone who quotes it. Short-range interactions. The premise fails here. So instead of the mode's energy sliding to zero as the wavelength grows, it saturates, at the plasma frequency of the metal, several electron volts. The would-be gapless mode is not softened or damped. It is thrown to the top of the spectrum, thousands of times higher in energy than the gap.
What happened to it, though? A mode does not evaporate. Something has to be carrying that degree of freedom.
The photon is carrying it, and this is the sentence to keep. A magnetic field inside the superconductor dies exponentially over the penetration depth. Now ask what kind of force has a field that dies exponentially with a fixed range rather than falling off as a power. That is what a force carried by a massive particle looks like. The range is Planck's constant over the mass times the speed of light. So inside a superconductor, the photon has acquired a mass, and 1 over that mass is the penetration depth. 16 nanometers in aluminium is a photon mass of about 10 electron volts.
The Meissner effect is the photon mass, not a consequence of it. The same statement, seen from the field's side rather than the materials.
The same statement, and the bookkeeping closes exactly. A massless photon has 2 polarizations, both transverse. A massive one has 3, because it can now vibrate along its direction of travel. Where did the third come from? It is the phase mode. The symmetry breaking supplied a degree of freedom, and the electromagnetic field absorbed it. Philip Anderson wrote it down in 1963 in Physical Review under the title Plasmons, Gauge Invariance and Mass.
And this is the mechanism particle physics took.
The relativistic version came the following year. Englert and Brout, then Higgs, then Geralnik, Hagen and Kibble. And Higgs's paper cites Anderson's. The weak force is short-ranged because its carriers are heavy. They are heavy because a field with a wine bottle-free energy has a non-zero value everywhere, and the gauge bosons eat the phase modes. Every structural element of that was worked out first for a cold metal expelling a magnetic field.
You have said all hour that the phase itself is unmeasurable and only differences matter. Is there an experiment where a phase difference is the whole apparatus?
There is, and it is the most consequential device in the subject. 2 pieces of superconductor separated by an insulating barrier a nanometer or 2 thick, thin enough that each order parameter leaks into it, and they overlap. Each side has its own phase. Brian Josephson, a second-year graduate student at Cambridge, asked in 1962 what current flows across that barrier. And the answer is startling twice over.
Startling how?
First, a current flows with no voltage across the junction at all. Not a leakage, a genuine supercurrent, pairs crossing the insulator coherently. Second, its size and direction are set entirely by the difference between the 2 phases, going as the sign of that difference. Set the phases equal and nothing flows. Push one ahead of the other and current flows one way. Push further and it reverses.
And if I put a voltage across it, the 2 condensates are at different energies. A quantum phase advances at a rate set by energy, so the 2 phases would start winding at different rates, and the difference would grow steadily, which through the sign makes the current oscillate rather than flow.
Oscillate at a frequency proportional to the voltage, with a constant of proportionality containing the charge of the carrier. The two again. 484 megahertz for every microvolt. That is a radio frequency you can count against an atomic clock, produced by a voltage, and since the redefinition of the units in 2019, the volt is realized exactly that way. Bardeen publicly disputed it. Anderson and Rowell saw it within a year. Josephson had the Nobel Prize in 1973.
What does it become when you put two of them in a ring?
A magnetometer that counts flux quanta. Two junctions in a superconducting loop, and the current through the pair depends periodically on the flux threading it, with a period of 1 quantum. So you interpolate within a period and measure far below 1. A squid resolves a few femtotesla against the Earth's 50 microtesla, which is how the field of currents in a living brain is read through a skull.
The ceramic in the dish, though. Everything we built runs on phonons, and it delivered a few Kelvin. That disk works at 93.
Georg Bednorz and Alex Müller at IBM Zurich, 1986, found an onset above 30 Kelvin in a lanthanum barium copper oxide, a ceramic in a class nobody expected to conduct at all. Nobel Prize the following year, which is close to unprecedented. Within months, Mo Kuen Wu at Alabama and Paul Chu at Houston put yttrium in place of lanthanum and got 93, above the boiling point of nitrogen. The mercury cuprates reach 133.
And BCS does not explain it. Say where it breaks, precisely, because high-temperature superconductivity is unsolved, is a slogan, and I want the specific failures.
4 of them, and none is a matter of adjusting a coefficient. The transition temperatures are far above anything the phonons of a copper oxide can produce. The frequencies are measured, the couplings are measured, and no exponential you're entitled to write gets you to 93. Hydrogen squeezed to 1 million atmospheres does beat that on phonons alone. A cuprate has no such mode in it. The parent compounds are insulators, but not band insulators. They have a half-filled band and would be metals if the electrons ignored each other, and they insulate because of the repulsion between them, so the Fermi C. Cooper's argument starts from is not there to be destabilized. The isotope effect is small to absent at optimal doping, and the gap changes sign around the Fermi surface, vanishing along 4 directions. A shape of phonon attraction, which pulls the same way everywhere, does not naturally produce.
What survives of today, then, when the material stops cooperating?
The pairing survives, and by measurement rather than loyalty. Flux quantization in a cuprate ring gives the same quantum with the same 2 in it. Whatever binds them, the things that condense are pairs of charge 2e. What does not survive is the glue and the starting point. 4 decades, no agreed mechanism. That is the state of it, and it is the subject of the last hour of this course.
I want to go back to the dish because I can now say what is happening in it. The ceramic is below its transition, so the electrons near the surface of the sea are paired, bound across nanometers by a positive wake the ions left behind, though nobody knows what the wake is in that material. The pairs share one phase across the whole disk. Most of the magnet's field is not expelled. It threads the ceramic in tubes, each carrying 1 quantum, and those lines are stuck on defects. The thin skin, where the field does die away, is dying because the photon is heavy in there. And what makes this a phase of matter rather than a wire with no resistance is that the field would have been thrown out even if it had got in first.
Which 2 of those could you defend against somebody who did not believe you?
The pairing, from 1 number. Walk a loop deep inside a superconducting ring where no current flows. Single-valuedness makes the phase wind by a whole number of turns. Gauge invariance makes the only legal quantity the phase gradient, measured against the vector potential. Zero current makes those 2 cancel, so the flux through the ring is a whole number times Planck's constant over the charge that carries the phase. and the period Deaver and Fairback measured, and Doll and Neubauer, is Planck's constant over 2 electron charges. That is a spacing, not an interpretation.
And the other.
That a weak attraction is enough, which I got wrong an hour ago. In free space, a shallow well binds nothing because the states you would build a bound state out of run out as you approach zero energy. Fill the sea and everything below the surface is forbidden, so the states you may use begin at the surface, where their number per unit energy is a large constant that does not run out. That turns the sum into a logarithm, and a logarithm has no ceiling, so it can always be made to match 1 over a small coupling. Any attraction at all destabilizes the sea. And because the answer is an exponential of -1 over the coupling, no expansion in powers of the coupling could have found it.
And the question you have that I have not answered.
Why the mean field treatment is allowed. Every step of the gap equation replaced the other pairs by their average, and Landau's expansion did the same at the level of the free energy, and that move was visibly wrong for liquid helium near its transition. Here it is not merely tolerable, it is nearly exact, and I think the reason is the length. The pairs are microns across, and millions of them overlap, so any one averages over a vast number of others, and the fluctuations are diluted. Ginzburg's estimate for where mean field theory fails in an ordinary superconductor was 1 part in a million of the transition temperature.
Which nobody will ever measure, and in liquid helium, the same criterion gives a critical region wide enough to see with a thermometer. 1 approximation, 2 verdicts, and what separates them is a length that grows as you approach the transition. Next time that length is the subject, and it stops being a technicality, because when it grows without bound, the system forgets what it is made of, and a magnet and a boiling fluid start giving the same answers.